Friends, welcome back to my YouTube channel. In this lecture, I am going to discuss about mixing chamber. This mixing chamber is such a topic from which questions have started to come, especially in GATE exam. So we can't afford to neglect this topic. So in this lecture, I will discuss what is mixing chamber, and later on I will solve a numerical on it after deriving the steady flow energy equation for this mixing chamber. Before getting into this, I must say one thing to all of you. Please do subscribe to this channel. Of course, like it and share it to your friends. So let's get started. In engineering applications, you will find the occurrence of two streams of fluids mixing with each other. This is a very common occurrence in engineering applications, and instances are so many, examples are so many where the mixing of two streams of fluids take place. Even in our daily life also, these things we find out. And when this mixing process takes place at a section, we call it a mixing chamber. So we can define mixing chamber like this. Mixing chamber is a section where two streams of fluid, there can be two or more streams of fluid mix with each other. So mixing chamber, as the term suggests, that does not necessarily mean that there is a certain chamber. As one would think that there must be a chamber within which there would be some mixing. Nothing like that. So ऐसा नहीं है. So mixing chamber जो है ये एक section है where two or more streams of fluid mix with each other. And examples in daily life are, suppose you must have seen in bathing shower, in winter days when the temperature is quite low. So the temperature of water is quite low, in which we cannot take a bath, especially in winter days where the temperature is quite low. So what will we do? We will use geyser for having some increase in the temperature of water. So how does this process take place? Suppose here you see this is a T section. Where here hot water is coming from geyser, and here the cold water enters into this section, and this section is called mixing chamber. And suppose this is 1 is the section where the hot water entering, and this is suppose 2 where the cold water or the normal water that is coming from the this side. So when there is when mixing takes place, and the whatever emerges, this is the suppose section 3, this is the out. Here this fluid mixes with this fluid, and this is the outgoing fluid. These two are incoming fluids. After mixing, this stream of fluid out goes or emerges. So it will be having a different temperature. Whatever temperature this water will be having, will be obviously higher than the temperature of this water, but this exit temperature will definitely lie in between. It will be less than this one and more than this one, because here that depends upon the whatever is the amount of water that flows in both these two streams. So we can after analysis we can find out the exit temperature, and while solving a numerical we will come to know how the exit temperature will be calculated. So how to derive the steady flow energy equation for mixing chamber? Just like we derive in every case, every device, maybe in case of nozzle device, nozzle diffuser, turbine compressor, we have already derived steady flow energy equation. Similarly, in this case also, steady flow energy equation can be derived only on two principles. One is principles of mass balance or mass conservation principle, and another one is the energy balance. So these two principles are the basis on which we can derive steady flow energy equation. Suppose this is our mixing chamber. ये हुआ हमारा mixing chamber. Suppose there are two streams of fluid entering into this. Suppose this is m1 dot, the mass flow rate of stream 1 entering into the, suppose this is mixing chamber, and second stream that enters into this is suppose m2 dot, mass flow rate. These are the mass flow. This m1 dot represents the mass flow rate of the stream of water that is entering here in this. This is the first stream. The mass flow rate of water that is entering is m1 dot, and suppose with enthalpy, suppose specific enthalpy h1, and in this stream suppose the mass flow rate is m2 dot, मतलब पर सेकेंड में इतना मास एंटर कर रहा है ये मिक्सिंग चैम्बर में, and with specific enthalpy of this stream of water is suppose H2. And here after mixing takes place in this mixing chamber, then the stream that out goes or emerges from this mixing chamber, that goes out of this mixing chamber, suppose mass flow rate is m3 dot with specific enthalpy H3. So now according to the principles of mass balance, we know that mass does not come from anywhere. Mass is always conserved, just like energy. Mass is always conserved. It cannot be created nor can it be destroyed. So according to the principle of mass balance, what happens? m1 dot plus m2 dot. This summation represents the total mass flow rate entering into the control volume or CB. Here control volume is mixing chamber. Since the mass interaction takes place between, this is suppose your system, and these masses are coming and this mass is leaving. So that means this is a control volume. This is an open system because the mass interaction takes place between the system and surroundings. So total mass flow rate entering into control volume is m1 dot plus m2 dot, and m3 dot is equal to mass flow rate of, you can take liquid, total mass flow rate of liquid entering into control volume, suppose, and m3 dot represent mass flow rate of liquid stream leaving the control volume. And according to mass balance, what happens? m1 dot plus m2 dot minus m3 dot represent d mass of control volume upon dt. पर सेकेंड में कितना मास इंक्रीज हो जाएगा इस कंट्रोल वॉल्यूम में, एक्यूमुलेशन होगा. ये तो m1 डॉट प्लस m2 डॉट एंटर कर रहा है, और उससे अगर m3 डॉट बाहर जाएगा तो जो नेट रहेगा ये ये होगा m1 प्लस m2 डॉट माइनस f3 डॉट इज इक्वल टू dmcv। कंट्रोल वॉल्यूम में पर सेकेंड में इतना एक्यूमुलेशन होगा और इंक्रीज होगा। लेकिन अगर ये स्टेडी फ्लो डिवाइस है, अगर ये स्टेडी फ्लो, ऑल दीज प्रोसेसेस आर टेकिंग प्लेस इन ए स्टेडी मैनर, then we have already discussed that in a steady flow process mass हर कोई प्रॉपर्टी बी इट एक्सटेंसिव और इंटेंसिव डज नॉट वेरी विथ टाइम। सो फॉर दिस वैल्यू इज इक्वल टू 0 for steady flow process. Since we have assumed that this mixing chamber operates in a steady manner, so that's why we can assume that dmcb upon dt is equal to 0. So from which what we found is m1 dot plus m2 dot is minus m3 dot is equal to 0, implies this is equal to m3 dot. Since this minus this is equal to 0, that implies m1 dot plus m2 dot is equal to m3 dot. This is your equation 1. And from energy balance another equation will emerge. What is this energy balance? Energy balance जो कि हमारा स्टेडी फ्लो एनर्जी इक्वेशन आएगा जिससे सो एनर्जी बैलेंस, वट एवर एनर्जी फ्लो रेट ऑफ स्ट्रीम्स एंटरिंग, एनर्जी फ्लो रेट समेशन ऑफ एनर्जी flow rate of all the streams entering into this mixing chamber is equal to energy flow rate of the streams of liquid leaving the mixing chamber. So you know that in this case, in case of a control volume, energy flows along with mass apart from the heat and work interactions. हीट एंड वर्क इंटरेक्शन सिस्टम और सराउंडिंग के बीच में तो होता ही होता है, जैसे कि क्लोज सिस्टम में होता है। अपार्ट फ्रॉम दैट मासेस के साथ भी कुछ एनर्जी एंटर करता है और कुछ बाहर भी जाता है। दिस मास ऑफ लिक्विड्स आर एंटरिंग m1 डॉट, उसके साथ भी एनर्जी एंटर्स, and with this stream of liquid also energy enters, and with this stream of liquid energy leaves the control volume. So we have to take all those factors into account. But while deriving the steady flow energy equation or energy balance, we have to assume that certain assumptions we have to make. What the assumption is, first assumption we have already taken, that the flow is, what are the assumptions? You see, assumptions are first assumption is steady, the process is steady. Then second assumption is, most of the cases this can be assumed to be insulated. Mixing chamber can be assumed. Here suppose the QCB is equal to 0. यहाँ neither there is some heat interaction into the control volume nor any heat is going out of this control volume. Suppose this mixing chamber is insulated, then and obviously there is no work जो शाफ्ट वर्क होता है एनर्जी एनालिसिस में, वी हैव ऑलरेडी डिस्कस्ड। यहाँ जो स्टेडी फ्लो एनर्जी इक्वेशन में जो WCB जो टर्म है वो रिप्रेजेंट्स द आइदर शाफ्ट वर्क और इलेक्ट्रिकल वर्क। हियर इन दिस केस देयर इज नो सच टर्म, सो दैट्स व्हाई WCB विल बी 0 ऑल्सो। एंड जो स्टेडी फ्लो एनर्जी इक्वेशन में जो टर्म्स रिलेटिंग टू काइनेटिक एंड पोटेंशियल एनर्जी भी होता है, usually what happens, those kinetic energy and potential energy terms are neglected, because if you compare those values of those energies, they more often than not they come out very less as compared to the specific enthalpy values of the corresponding streams of liquids. So that's how we can neglect the potential and kinetic energy terms. And supposing that this mixing chamber is insulated, and WCB तो 0 होगा ही होगा, क्योंकि there is no shaft involved here and nor any electrical work is also here. So that's why these things are coming out to be 0. So I can write the steady flow energy equation like this. Energy balance जो होता है E1 dot plus E2 dot माइनस E3 डॉट, जैसे मास बैलेंस में होता है ये भी एनर्जी बैलेंस में होता है, DEC भी डिवाइडेड बाय DT. Whatever energy entering into control volume minus whatever energy leaving in the control volume is equal to net increase in control volume, energy in control volume per time, but this term is equal to 0 for steady flow. So that implies E1 dot plus E2 dot is equal to E3 dot. And we know that for unit mass of fluid, what is the energy flow? Energy per unit mass of flowing fluid वो होता है m, जो थीटा लेते हैं हम, h plus v square by 2 plus gz. Since ये दोनों टर्म को हम नेग्लेक्ट करेंगे तो ओनली स्पेसिफिक एंथैल्पी विल रिमेन. सो दैट्स वाई E1 डॉट विल बी m1 डॉट h1, नेग्लेक्टिंग ऑल द काइनेटिक एनर्जी and potential energy terms, plus m2 dot h2 is equal to m3 dot h3. So this is equation 2. If this specific enthalpy of this incoming stream of liquid is small h1 and second stream of liquid is h2, then and the third stream, that is outgoing stream for the mixing chamber, m3 dot is the mass flow rate and h3 is the specific enthalpy, then this equation can be written m1 dot h1 plus m2 dot h2 is equal to m3 dot h3. This is equation 2 suppose, and equation 1 is nothing but m1 dot plus m2 dot is equal to m3 dot. And for deriving this, these are the necessary assumptions we have made, that flow is steady and this mixing chamber is well insulated, that's why Q will be 0, and of course there is no shaft involved, so that's why W control volume will be 0, no external work is there, and usually we can neglect the potential energy and kinetic energy terms because they are quite negligible as compared to specific enthalpy. So that's why this equation is derived, and using these two equations we can solve any numerical on the mixing chamber. Suppose this is a question which we will solve. So consider an ordinary shower, जैसे which is used in winter days, where hot water at 60 degrees Celsius is mixed with cold water at 10 degrees Celsius. Hot water at 60 degrees Celsius is mixed with cold water at 10 degrees Celsius. Of course, the whatever stream emerges out of this mixing chamber will be having a temperature in between these two values. It will be less than 60 and more than 10. It is obvious. It is desired that a steady stream of warm water at 45 degrees Celsius be supplied. So, but the desired temperature, ऐसा ही नहीं है, we cannot bath in a if the temperature of water is excessively high. So the temperature has to be maintained at a level such that we can take comfortable bath. So that's why suppose we desire the temperature should be at 45 degrees Celsius. At 60 degrees Celsius we may not feel comfortable, so that's why we want to keep it down to 45 degrees Celsius. So for that what we can do is we have to mix this hot water with certain amount of cold water of temperature 10 degrees Celsius. So determine the ratio of the mass flow rates of the hot to cold water. So हमको ये निकालना है the ratio of the mass flow rate of hot and cold water. Assume the heat losses from the mixing chamber to be negligible. That means that is an adiabatic mixing chamber. So heat QCB is given to be 0. Suppose in case of any problem, if it is not given to be 0, it has to be taken into account. So to be negligible, and the mixing takes place at a pressure of 150 kilopascal. So वाटर का जो प्रेशर है 150 kilopascal है. So here यहाँ लिखा हुआ है ना steady stream, so it is assumed that the flow is steady stream. So these are the key points. जो इनलेट वाटर स्ट्रीम 1 का टेम्परेचर 60, स्ट्रीम 2 का 10 और स्ट्रीम 3 जो निकल के आ रहा है उसका 45 डिग्री सेल्सियस है. सो हमको बस m1 डॉट और m2 डॉट, जैसे कि सपोज दिस इज द डायग्राम, दिस इज द डायग्राम. सपोज इसका टेम्परेचर सपोज T1 is 60 डिग्री सेल्सियस. Desired temperature is 45 degree Celsius, or suppose m3 dot is the mass flow rate of this outgoing stream of water that emerges out of this mixing chamber. हमको निकालना है m1 dot divided by m2 dot, इसका जो रेशियो है हमको निकालना है, ये निकालना है m1 dot by m2 dot. So since this process takes place in a steady flow, this process is a steady flow process, so that's why we can assume that delta M of control volume is 0, delta E of control volume is 0. Whatever assumptions we have already made for deriving steady flow energy equation will hold good in this case also. And since there is nothing written about the kinetic energy and potential energy of liquid streams, so we can neglect it to be, and we can assume it to be negligible or 0. So these things we can assume, and Q also 0 is equal to WB 0. Q dot and W dot दोनों 0 है. So just we derived those two equations, and all these things were holding good for that case. So that's why whatever equations we derived, that is first equation is m1 dot plus m2 dot is equal to m3 dot. Suppose this is the equation, first equation. We just derived it according to a principle of mass balance. This is the equation, m1 dot plus m2 dot is equal to m3 dot. And the second equation that we derived is m1 dot h1 plus m2 dot h2 is equal to m3 dot h3, where h1, small h2 and small h3 are the specific enthalpies of the streams of liquids 1, 2 and 3 respectively, specific enthalpy. So from these two equations we can find out the ratio, that is m1 dot divided by m2 dot. Suppose what I will do is, this m3 dot is nothing but m1 dot plus m2 dot. By substituting this value of m3 dot in this equation, substituting the value of m3 dot from equation 1 in equation 2, I can write like this: m1 dot h1 plus m2 dot h2 is equal to, in place of m3 dot I can write m1 dot plus m2 dot. There is no problem in it. From which I have to determine m1 dot by m2 dot. So dividing both sides of equation 2 by m2 dot, we get, so m1 dot divided by m2 dot h1 plus m2 dot h2 is equal to m1 dot plus m2 dot by m2 dot h3. Let m1 dot by m2 dot is equal to x, which is required to be found out. This one we want to find out, m1 dot divided by m2 dot. ये पूछा है ना, रेशियो ऑफ मास फ्लो रेट्स ऑफ द हॉट टू कोल्ड वाटर. ये हॉट वाटर है 60 डिग्री सेल्सियस टेम्परेचर में है और ये कोल्ड वाटर है. सो वी हैव टू फाइंड आउट m1 डॉट, रेशियो ऑफ m1 डॉट एंड m2 डॉट, m1 dot divided by m2 dot. So let it be x. So now this equation reduces to x h1 plus m2 dot divided by m2 dot is 1. So that's why h2 is equal to, this one will become x plus 1 h3, x plus 1 h3. So now the equation 2 is like this, x h1 plus h2 is equal to x plus 1 h3, from which I can find out the x h1 plus h2, x h1 plus h2 is equal to x h3 plus h3, or x h1 minus h3 is equal to h3 minus h2. So x is equal to h3 minus h2 divided by h1 minus h3. Suppose this is equation. So now the question is reduced to just finding out these three values, h1, h2 and h3, so that we can find out x, that is the ratio of m1 dot and m2 dot, the mass flow rate of hot water stream and mass flow rate of cold water stream. So just by finding out the specific enthalpies of three liquid streams, we can find out this. So how to find out the specific enthalpy of three liquid streams? You see, pressure of water in all these three cases, in the pressure of water that is flowing through this mixing chamber is constant at 150 kilopascal. जो भी वाटर एंटर कर रहा है या लीव कर रहा है, कोई प्रेशर ड्रॉप नहीं हो रहा है. Pressure remains constant throughout at 150 kilopascal. And we know that saturation temperature of water at 150 kilopascal, which is slightly above the atmospheric pressure, is 111.35 degrees Celsius. But all these temperatures are below that temperature. You see here it is 60, it is 10, it is 45. So obviously it is well below that saturation temperature. So that means in all these three cases, water is in compressed liquid state. And all these things you will cover while studying pure substance. You will get a better understanding. But that means here water has not started to vaporize. You must know that water is in a compressed liquid state. At saturation temperature, liquid starts vaporizing. So water is in compressed liquid state. And in compressed liquid temperature, or in compressed liquid state, a liquid can be approximated as saturated liquid. A liquid can be approximated as saturated liquid. So enthalpy values for saturated liquid will be applicable for this case also. So compressed liquid can be approximated as saturated liquid at given temperature. So compressed liquid, whenever the temperature of any liquid is less than its saturation temperature at a given pressure, then it can be considered as a compressed liquid, and compressed liquid can be approximated as a saturated liquid at a given temperature. गिवन टेम्परेचर मतलब सपोज हॉट वाटर स्ट्रीम जिसका टेम्परेचर है 60 डिग्री सेल्सियस. सो उसका स्पेसिफिक एंथैल्पी लिक्विड स्टेट में हम स्टीम टेबल से वी कैन फाइंड आउट फ्रॉम स्टीम टेबल. अदरवाइज वी कैन कैलकुलेट लाइक दिस. सपोज H1 is nothing but HF1. What is HF and Hg you will come to understand in a better way while studying properties of pure substance. But the values can be calculated in this. So since this is the liquid is in compressed state, so it can be approximated as a saturated liquid and for a given temperature. Suppose here hot water stream is at a 60 degrees Celsius. 60 degrees Celsius. Just like ideal gas, H can be calculated as Cp or Cvt. Both are same, Cp or Cv multiplied by T. For an ideal gas, H is equal to Cpt and U is equal to Cvt, where Cp and Cv are specific heat at constant pressure and specific heat at constant volume respectively. But for liquids, these two values are not different. Cp and Cv assume same values since liquids are incompressible. So both the values are same. So that's why H1 is Cp or Cv, which is 4.187 is for water multiplied by 60. Temperature of hot water stream is at 60 degrees Celsius. So this comes out to be 251.22 kilojoule per kg. This is H1. Otherwise, you can also refer to steam table where you will find that HF at 60 degrees Celsius temperature. HF at 60 degrees Celsius, saturated liquid at 60 degrees Celsius. If you refer to, then you will find the value. So this is 251.22. And for H2, H2 means this is at second stream, cold water stream is at 10 degrees Celsius. So that is 4.187 multiplied by 10, that is 41.87 kilojoule per kg. Then the third value, that is H3, is equal to 4.187 multiplied by 45. This is the desired temperature. 45 is equal to 188.415 kilojoule per kg. By putting all these three values in this equation 3, we can find out the desired answer. X matlab m1 dot divided by m2 dot, which is required to be found out, is equal to H3 minus H2. H3 minus H2. H3 here is 188.415 minus H2 is 41.87 divided by 251.22 minus 188.415. This is kilojoule per kg. This is also in kilojoule per kg. So this will come out to be 146 0.545 divided by 62.805 kilojoule per kg. This is also in kilojoule per kg, and this will be 2.333, or we can say m1 dot is equal to 2.33 m2, but the ratio was asked to find out, and that ratio of hot water, the ratio of flow rate, mass flow rate of hot water stream and cold water stream is 2.33. so ज़्यादा hot water को flow करना है. So and m1 dot will be 2.33 multiplied by m2 dot. So this is the answer.